appreciate this. I think I have to do. Got it. No, much appreciate this opportunity, and happy to share our experience about the metamaterials in general, but in particular on the design aspect, industrial challenges. This is basically the core of our activities here in Phononic Vibes. The presentation is about as basically 5 chapters. Okay, short introduction on who we are, what we do. Then it's divided in 3 sections: metamaterial for infrastructure, transportation, and appliances, and then a short summary. But this in the chapter on the section 2, 3, and 4, there are core applications on these three sectors in which we actively work. I'll try to cover everything in 40 minutes. If I am slower than that, please let me know, especially if you have some time constraints after 11. So a few words about Phononic Vibes. We are born as a spin-off of Politecnico of Milano, so as a startup, but in principle, we are a deep tech company. So we make hardware. We don't make software at the moment. We focus on the art of noise management. Basically, we deal with everything that is related to noise, but as well as vibration. And in particular, with our metamaterial technology, we work for controlling the absorption and isolation inside the medium. It can be the air, but as well as can be in the structure. Why then we chose to focus on noise or vibration? Because noise is basically everywhere. You can find it at home, so as an annoyance while traveling in cities. It is responsible of a lot of health-related issues. Therefore, controlling the noise or reducing the noise and the vibration can bring overall benefits as well as health benefits, as well as reducing the annoyance of whatever system that creates this noise. Therefore, our motto, our vision is the art of noise management. Therefore, we through our experience in noise vibration related say subjects, we developed effective, affordable, and sustainable solutions based on the metamaterials, relying on existing materials or new structures or new materials. How did we do so throughout the years? Okay, we developed different applications. Therefore, we have 15 patents portfolio for different sectors. But aside all these words, maybe it's worth to spend a bit of time to discuss what metamaterials are. Probably I'm going to ask all of you, probably you're already working on metamaterials, most likely. Therefore, and some of you are from Greece, so if I say metamaterial, that is actually a Greek word, it means beyond materials. Therefore, this is exactly, let's say, the meaning of metamaterial. So we are not inventing a new material, but basically we are creating a new structure. So we are modifying topologically the structure in order to control the propagation of energy in the structure. If you can control the propagation of energy in the structure, therefore we can block it or we can deviate it, we can modulate it, and so on. Before continuing, I want to ask all of you, you are experiencing metamaterials, or for you is something new, or you just started, or?
No, the group has, like part of the group has worked with metamaterials, but not like the whole group. So
not totally.
Your introduction.
So maybe I can spend a few more words, but in general, for metamaterials, it is intended all this type of structures where you can, as I said, change the topology, change the shapes to create local resonances, or you can create scatterer to control the wave propagation. So for these local resonances, for instance, in these pictures, you can see some features that have been designed with an endpoint mass with a slender body that works as a mass spring structure, or that can work like really a bulky structure scatterer. And this is an example how structured metamaterial works. So we create local resonances in the structure, and these local resonances interfere with the incident wave, and therefore you can block it or indeed control it. That's the right word. This is for the structure. For the acoustic is very similar. Instead of creating structure appendix structural features, you create acoustic features. So therefore cavities, labyrinth shapes, voids, and so on, that they create an acoustic resonances, and then with in the same principle, you can control the wave propagation. This is really, in a nutshell, what metamaterial, the structure of metamaterial look like. But if you look at this cube, you say, okay, nice, this is a cube. It's being 3D printed, but how do we scale it from a concept, so a low TRL, low technology readiness level, to a higher TRL? So like a higher TRL means that in a product, and normally the TRL goes from zero, from one, which is basically an idea, a concept, a sketch, a drawing on a paper, to 9, which is basically your final product that you can buy. So the question is, how did we scale up from a low TRL to make metamaterials into product? This is really the focus of our company and what we are working actively, say, every day. So we started from the cube, and then we reshaped it, we remodulated it, we changed the topology in order to make, for instance, barriers, different shapes, or other types of products. Well, first of all, the company needs to be ready for preparing this product. So legally, it needs to have some bureaucratic stuff, for instance, certification, which is really important for companies. But aside from this, um, uh, you need to focus on certain sectors. So we decided to focus on 3 verticals: the infrastructure sector, transportation sector, and appliances sector. Each of these sectors, so we segment it, we divide it, because each of these sector has its own features. So the type of material that it is possible to use, the type of problems, and the type of manufacturing aspects. Therefore, yes, the performance of metamaterial is exactly, let's say, what we are looking for. So we are looking for a new technology that is much more performant than the current technology, and therefore we can reduce the noise or the vibration in an outstanding way. But then we need to face with the costs, with the material, the manufacturing aspect, which, let's say, if we segment in this way, is really sector specific. In this presentation, I tried to give you an overview of how we deal with it. And probably that can be, let's say, a trigger for for you, for everyone, for the community to stimulate, to make sure that when you design a new metamaterial solution, or when you work for a new metamaterial solution, if you put also all these 3 parameters in your metrics, and then you optimize it in a general sense, you don't look only at the performance, but you can look also at the design that includes the cost, the material, the manufacturing. Therefore, you create a system or a solution as an overall, it is already ready for being commercialized. But to get to that, let's start step by step. So for instance, let's start with the infrastructure sector. So for the infrastructure sector, we work in 2 directions. We work for reducing the vibration, the ground bore vibrations, or to reduce the airborne emissions from, in this case, from railway noise. Let's focus on the vibration. So we developed a product which is called Meta Vibration. What does this product do? So probably you're working on something similar, but what did we do? So we have a vibration source. In this case, is the train on the railway track is creating a different type of waves, surface wave, PNS waves that travels into the soil and then can damage or create annoyance in the buildings. So typically, you create okay, some solutions into the foundation, so you create trenches. These trenches are very useful for blocking surface waves, for instance. But there is a problem with the trenches. Trenches are holes into the ground, so they are dug up to block, to create an interruption of these waves from the receiver, from the input to the receiver. And therefore, it's not always, say, safe to have a hole into the ground, especially if there are some machineries that need, or cars that need to pass along that way. Therefore, instead of the trenches, typically they use some decouplers like U shape or inverse U shape that can still work as a decoupler. But the question is, can we do better? Can we trigger resonances inside these decouplers to increase the isolation from the source to receiver? This is exactly was the first question. So the the objective. And then in terms of innovation, we create a solution to improve the isolation at low frequency, and especially the annoyance, or at least the problem is located around 30 Hz. And the main challenge is to integrate this resonance structure inside this solution. And aside from this, the resonance structure needs to have a bare load capacity. Therefore, heavy structures needs to make sure that they can pass over this solution. And also the cost of the material, the manufacturer needs to be aligned to what there is at the moment with the current in the current solution. So where did we start? We start exactly from the unit cell. We start exactly from design which looks really similar to the cube that I showed you at the beginning. And through stop band analysis, we design features inside this cube, so resonant features that can enable a stop band, a very large stop band, um, in, uh, in in the frequency that we are looking for. Is pretty much low frequency. Therefore, in all this range, we have no wave propagation. Therefore, we can block the energy propagation there. Therefore, if we can block the wave propagation, we can make sure that the energy from left to right, so from one point to the other point, is not passing, and therefore we can maximize the insertion loss and the isolation in this frequency range. From the unit cell, we created this cube that you saw it in the pictures, and then from the cube, we tested in the lab, so with a sensor, an actuator, and sensor to verify that the stop band is according to what we have designed it for. And then from the concept, from a low TRL, we made the first prototype. The first prototype, which was made with the same material as the final solution, and which material we have chosen for the purpose. We have chosen concrete and steel, because in the infrastructure sector, metal and concrete is basically what is used the most. But you can imagine that we need to create a resonance structure made of concrete and steel. How did we do that? We use the steel as a spring and the concrete as a mass, which would have been the most logical thing to do, of course. But this had to be, let's say, of course, tuned as a first thing, and secondly, needed to be molded. Then the mold was one of the key points for the manufacturing aspect, because it's what creates and leads to the final product. So we create the solution, we test it, and the solution is behaving according to what we were looking for. So the first, I mean, the cutoff frequency start from 30 Hz onwards, And then we inserted these blocks inside this structure, and this structure mostly serves to preserve that the dirt, the ground is touching the resonators and is blocking the resonator to vibrate. This is the reason why we encapsulate this array of resonators inside this block. With the simulations, we can demonstrate that if we have a train track here, an excitation that comes from the train, and then we have, let's say, of course, the vibrations and as well as the energy propagation that can freely travel. When we add the blocks, we can block and we can really increase the insertion loss from left to right uh, from these trenches, from this solution. Of course, we can block the surface wave, but the wave that travels underground, they are more difficult. But it is at least a good achievement and not too much invasive solution to be applied for controlling the ground bore vibration. Another aspect is, okay, we create this amazing solution. Now this needs to be installed. So you can imagine that when you design and then when you make all the numerical simulations for your solution, you never imagine that there is a person that afterwards will take your solution and I will throw it into the hole, into the ground with the legacy of, they are not really taking care too much of the solution. They take a crane, they drop it into the ground, and then they put all the dirt next to it and then say, okay, they decide they has to work. So they don't really care too much on how to treat them. Therefore, what I'm saying with this, I'm saying that when you're designing a solution, you never imagine that you need to also design it that it needs to be robust enough, not only to work as intended for blocking the vibration, but needs to be robust enough to withstand potential, say, people that take this and while install it, they're not really delicate. So this is another aspect that sometimes for a designer, for an engineer, especially if it's focused only on vibration and noise and vibration is not really taken care of. But an example is exactly, this is a classical example that is not the environment which this solution will be installed or is installed is not the most perfect environment as a lab environment. Aside from this, we did some in-situ installation, and we installed, for instance, here in Florence, we installed under the sidewalk in front of the church of San Marco in Florence. We installed the solutions, and we could create an insertion loss, so a reduction, vibration reduction from one side to the other side up to 14 dB. Therefore, this has been used to reduce the excitation and the vibration that travels into the old building of this church, so to preserve the 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 building from potential damages that can come from the structure that could come from the passage of the vehicles in front of the building. Question so far, but I wanted to give a thorough overview on, say, what could be the thematics of this specific solution. Now I'm going to go a little bit faster for the other applications, but in principle, the workflow that we use to develop new applications is exactly similar as the one that I just described. If there are no questions, I'll move on.
May I interrupt a bit, Luca?
Sure, Vasilis.
So if you don't proceed, let's say, in other classes of applications, I was wondering. I mean, this is very obviously very interesting. I was wondering if you consider, let's say, other sources of excitation, which are, let's say, low frequency, quite low frequency, such as earthquakes. Would, let's say, the design be much different in the sense that I suppose that you will need much larger masses, no?
Exactly. This must the point here is that the resonators or the resonances needs to be triggered as such that can be pushed in the lower frequency as possible. So let's say that you have an excitation of 2 hertz. You need to make sure that the mass at least resonates at 0.5 hertz.
Yes.
So if it's 0.5 hertz, you need to make sure that it's even lower. So at the end, you start to have a, yes, that's correct. As you said, you need to have much larger mass. But you are in a certain sense in a threshold in which the structure can really withstand or self-support itself.
Exactly. Exactly.
Yeah.
Exactly.
Probably this design is not really the most effective for earthquake. There could have been other type of more intelligent design, but typically the principle is similar. That's correct.
Okay. Okay.
Okay.
Thanks.
No, thanks. So now we have discussed so far about ground-borne vibration. What about airborne vibration? Airborne noise, sorry. So this is a typical noise, for instance, in infrastructure that could arise from the passage of a train. And normally for these solutions, you can find it if you travel on a train, or for sure you have seen it also in the highway. Um, there are transparent barrier, but as well as there are barriers that are not transparent. They are, let's say, full, which is different from left to right. Left, so the transparent barrier is a barrier that yeah, allows you to see the landscape, but doesn't absorb the noise. It reflects the noise. So the wave hit the barrier and then they're pushed back. For the full closed barrier, there inside you don't see the landscape, okay, but you have the possibility that the sound hits the barrier. Okay, part is pushed back, but 90% of the sound is absorbed because inside there is phone absorbing material, so absorption material that dissipate the noise in terms of thermoviscous losses. The question is now, is there a solution that we can design that enables us to see the landscape? So it is transparent, therefore it doesn't have an urbanistic impact, but at the same time doesn't reflect only the sound, but absorbs the sound. So can we make a transparent barrier that also absorbs like a full barrier? There was actually the question that has been raised by the Deutsche Bahn, which is the German railway company, and then we worked towards this design, which we have. It's called Meta Window. Our product, basically, it is a solution that we are producing here in Milano. So we have a manufacturing plant that is producing this this window, this Meta Window. Therefore, it is 70% transparent, so you can see through, but also combine high absorptions. High absorption, what does that mean? Means that in the railways or typically also in highway, you have a reference curve for isolation for absorption. If the performance of your solution is above this reference curve, therefore is considered high absorption. So according to their standard, this this meta window behaves as absorptive as the full barrier. But here the main challenge is how do we integrate, or how did we integrate metamaterial, so this resonance structure, into a transparent barrier? And another challenge, which is even more important, is the cost, the material, the manufacturing. Sorry, as before, because for the first challenge, okay, you can design for it. Of course, you know that the more transparency you have, the less material you have for absorption. So it's a compromise that it's a good balance that you need to find with a good strategy, good design strategy. But here, cost, material, manufacturing is everything related about the industrialization. And the industrialization is a core, as is core for the other product, but here specifically because in the market, this barrier, they must cost around 400, 500 euros per square meter. So you need to make sure that if you want to be competitive and you want to make sure that this solution reaches the market, this needs to be designed in a most easiest way. It needs to be used the most easy material, let's say, the most simple material, the common material, to make sure that you can be competitive and you can land it into the market. Therefore, here, what did we do? We tried out different shapes. We start from the cube. We had to enable, for instance, first of all, the resonances. So we need to first of all reach the target for the acoustics, and then afterwards we needed to make the system. Hexagonal shape was a perfect design, really amazing design to work and to achieve very good performance, but it was very difficult to make it, very costly. Therefore, we redesigned everything in a sort of linear shapes that could have been used, that could have been manufactured by extrusion, and extrusion is a manufacturing process that is much simple, and it's more cost effective than this type of process. Therefore, once we have the design that has been validated in terms of performance, and these are tests that we made in reverberation chamber to verify the isolation, but as well as the absorption of the meta window. There was one test that took us almost 1.5 years to pass, which is the fatigue test. So you have an amazing product that works for isolation, an amazing product that works for absorption, but then you have a block that is basically the fatigue test that had to run for 6 months. We failed it 2 times, almost at the end of the fatigue test, because of a small crack that opens up next to a screw that wasn't tight very good. And the fatigue test is fundamental, because you need to imagine that this barrier needs to resist 50 years, needs to last 50 years in the next to the train track, and needs to withstand the pressure load of a train running for 300 kilometers per hour close to the barrier. So you have a suction pressure, and that overloads the huge panel of the barrier, so it needs to withstand all this cycle of fatigue. So once again, here you are designing for metamaterials, but afterwards there are some other engineering, let's say, problems that needs to be taken into account, therefore needs to be added into design. And with the message, what I'm saying is that when you design for a nice solution, there is not only vibration and acoustic in this sense for metamaterial that can really make your system great, but there are, let's say, other 90% of things that probably, until your solution doesn't reach the let's say the final industrialization, you don't even see it. So with this message, it's like, if you're designing for metamaterial, or if you're designing for other solutions, make sure that you are trying to look also for other type of engineering problem that may arise, because they can potentially block your design. But in case, let's speak about something nice. Of course, this is everything nice, but there have been, of course, hiccup in the journey. So this is an example of a barrier that is inside the city. And of course, this is something that the citizen doesn't really want, because it blocks the view. It's not really nice. Therefore, we have substituted with our meta window. Of course, this is a render, because the guy here that he was still running in the same place. But it is a render. This actually has been already installed. So if you are in Germany, around Munich and Hamburg, you can see it. This installation live. There are also some pictures on LinkedIn and on the website of Deutsche Bahn about this new product. So after a lot of effort, that has been a reality. That's what I'm saying. So what has been our journey? So we had our objective, which we wanted to design some high performance absorption isolation solutions, metamaterial solutions for infrastructure. We have came up with two solutions, which are the meta vibration and the meta window. For infrastructure, specific for infrastructure, we have seen that concrete and metal is what is mostly used. But why is that? Because of course the infrastructure understands in terms of material mostly this type of materials because they are cheap, they are easy to retrieve, and so on. And for manufacturing, manufacturing has been really a key point to keep the costs low. For instance, in this case, for this solution, we use casting, extrusions, milling, a laser cut to make the product. And in this way, we could make the product. It could have been cost effective compared to standard solution. We could push it into the market. Otherwise, what happens is that you might have the most outstanding product in terms of performance, but it costs too much, and basically it doesn't see the reality. That is unfortunately the wrong side of the medal, the bad side of the medal. Okay, this is the infrastructure. What about the transportation? I don't know if there are questions so far, but otherwise I can continue. Okay, we can push the question at the end. So the transportation, let's say it is another word. So why it is another word? Because in transportation, here we are looking for different type of solutions, or at least what the transportation wants something that is lightweight, something that is super high performant. And of course, in transportation, you don't use concrete, and metal, yes, but you don't use concrete. Which type of material you use in transportation? So you use fibers, you use rubber, you use polyurethane foams, and so on. These are typically the material that you use. So lighter material than, of course, concrete. And in transportation, we are working a lot, say, in automotive, for instance, with Mercedes, with Ferrari, Bugatti Rimac, and Nissan. So we are working with several companies, and specifically with Mercedes, we have designed, we have engineered, we have produced a new solution which is called Meta Design. A fun fact about Meta Design, this is the name of the product we have, is that we did not call it anymore Metamaterial, but we had to call it Meta Design to hint that when we first present the Metamaterial solution, people thought it was a new material, although we explained that it's not a material, it's a design. It's a different topological design. Therefore, it was a Friday afternoon, I remember, that we have been called and asked for 2 kilos of metamaterials to put in their car. And we had to explain it several times that it's not a material. We cannot give them a material because it doesn't exist a material. It is a design that we need to make it, we need to engineer to make sure that afterwards, once it is in the car, it works properly. So we cannot have, say, a stock from this design and we can throw it. Therefore, the first problem there was a communication problem. So from metamaterial, we passed to meta design. That thing, at least we solved it. Then which type of design we engineered here? So we started from understanding which is the type of problem that we can address here with the metamaterial. So first of all, for instance, if we take a car, we have different type of energy transfer path or noise transfer path, or vibroacoustic transfer path, let's say in general. So we have powertrain noise, road noise, wind noise. One of the most annoying noise, especially for not battery electric vehicles, but internal combustion vehicles, is the powertrain noise. Here you have firewall, which is a metal part that divides the engine compartment to the interior compartment. And this firewall basically is a wall. And on top of this wall, there is this sound package. This sound package typically is quite heavy. If we look for the one for Mercedes, for instance, you have 10 kilo of located only in this area, and then you say, okay, 10 kilo on a car that weighs almost 2 tons. What is the matter? But actually, it is the matter, because every kilo that you reduce, you can reduce a lot the emissions, the CO2 emissions. So every kilo, actually every gram in a car is important. That's why there is the trend that you find more and more in your vehicles that there is only the screen with lots of features, and you don't have buttons anymore. So they remove the buttons to reduce even further the weight and the cost, of course. So this is crazy if you look at in terms of relative weights, 2 ton of car, and then you reduce 1 kilo. Yes, because 1 kilo counts a lot. So we focus on this inner dash, which is the solution that goes into the firewall. And the objective is to reduce destruction by vibration, improve isolation, and reduce weight. So it was quite challenging, the objective that we needed to address. And the innovation is to come up with an innovative lightweight acoustic pack based on metamaterials in order that it is acoustically more efficient. You can imagine that the main challenge here is the integration of the metamaterial with the current solutions, and especially here we are speaking of mass production process and about 1 million vehicles per year. So the cost even more needs to be maintained, it needs to be easy manufacturable and robust enough that for the speed of manufacturing process needs to be make sure that once enters into the car works as intended. Just to be clear, the standard design here, which said is standard material as polyester fibers or foam and so on with rubber, there's been a material that has been used for years in automotive. So there is a bit of inertia also in the changes of this type of manufacturing, this type of material. Therefore, we said, first of all, in the design of the solution, we will not change the material. This is a strength of metamaterial because you are not changing the material, but you are integrating a design into a current material. And this strength enables us to maintain the manufacturing process, maintain the materials, and therefore to roll out the solution in a faster way. And how did we design this? We designed it in such a way that we create local resonances, so distributed lumped mass spring systems into the design. And this has been, each of these resonances work at a specific frequency. Typically by design, we try to make it work in a specific frequency that opens up a stop band, so a frequency range where we can improve isolation. And in this specific design, we worked if you look at the transmission loss of the material, the classical curve of transmission loss, we work at the mass spring mass resonances, where the transmission loss is minimum. We maximize it, the performance, specifically in that frequency. This is typically a problem for low frequency, and this type of solution is really well suited for addressing the low frequency isolation of vibration. Therefore, we can have two types of design with this design. We can have a lighter design up to 30% lighter with the same acoustic performance as the current design, or we can have an equal mass design, so a solution with an equal mass, but we can boost the acoustic performance up to 3 dB. 3 dB means that you are reducing by 50% roughly the noise perception inside for the specific noise, which is a lot. It's something that you can hear. And we started from a 2D design, from the unit cell 2D design, and then we applied it on a 3D element, say, which is basically the inner dash element in a car. And we tested in a car. We did lots of tests on the bench, on the couple chamber, on the vehicle while driving. And afterwards, we had to integrate it into the industrial process. In this case, the industrial process is called a SIM, compound injection molding, which basically is an injection molding. Just to give you an idea how the final design looked like, this is a section of the real 3D design that is now in production for Mercedes. The blue part is the APDM, so it is the rubber. The violet part is the polyurethane foam. Here, the functionalization, so the metamaterial feature is a combination between this cross-like shape and the PDM, which is a bit outside, a bit inside the foam. And this, you can see it a little bit in the shadow and the transparency, translucency, this square section. So basically the combination between this mass or added mass and this square section, square cavity inside the foam leads to the performance that we have designed it for. So this is the final product. And to give you an idea how fast is the production of this material, this is a video that the part is injected, then is taken from a robot, carried away, and then you start with another injection. So the video was sped up by 2.5 times, but okay, this is not that slower than actually the video looks like. Just to give you an idea on how a simple design that you make on console, on your FEM model, then afterwards needs to encompass lots of certification and other aspect that the industrial environment afterwards needs to withstand the industrial environment, or for instance a product, a robot that takes with the pliers and then taken out from the mold and so on. So this meta design, basically, of course, we are the engineer company that designed the system, but for production, we did a partnership with a tier 1 supplier, which is Adel Group, and they have the warehouses and the industrial plants all around the world. We are not there yet, so we don't have the plants all around the world to make the production for Mercedes. But thanks to this collaboration, we could bring the solution inside the new Mercedes CLA. So if you're curious enough, you can buy your CLA, you can strip it down and look for the metamaterial solution. Okay, so what did we learn here about this market segment? It's very different from the infrastructure. Here we are looking for performance and lightweight design. The typical material is not anymore concrete, but it's rubber, foam, polyester fibers. In the manufacturing process here, we are going more towards injection molding, foaming, stamping, and so on. The cost is really fundamental here for automotive, and the cost needs to be compared to the standard product. And so if for the meta window, for the infrastructure, the panel needs to cost about 500 euro per square meter, this is roughly the price. For the automotive part, that part that we are making costs about 80 euro, maybe 5 euro. So it's really 100 times less.
Can I ask a question before you move forward?
Sure.
You said before, if I'm not mistaken, that there are you had like two solutions. One was like same material, but more noise, the reduction. But on the other hand, you could have like less material, but same like noise level reduction. What is the one that is usually preferred by the company? Since you said that
you're fading a bit. Your voice is fading a bit. I cannot hear you really well.
Okay. I will try to speak up.
Now it's better. Now it's better.
Okay. I don't know if you heard my question. I was saying that you said before that you were suggesting two solutions. Like one was more lightweight. Yes.
This one.
But the acoustic performance was better, and the other It was the same, and then for the same mass, you had like an enhanced acoustic performance, which is a solution that is typically preferred by the automotive companies.
Um, that's a very good question. Typically they always try to go for solution A, but there are
Okay.
premium cars. For instance, for Mercedes, there is the S class or the Maybach that are kind of limousine. They are really crazy cars for rich people. They look for comfort. So if you look for
Okay.
comfort, you can do for option B. But let's say 80%, 90% of the time they go for solution A because, as said, they try to reduce as much the weight, reduce as much the material that you're using in the car, but still maintaining the equal acoustic performance.
Okay. Okay. I see.
Uh,
No, I guess you can continue with like we should be able to wrap it up until 11.
Yeah,
So
I'll be really quick for this one, and then I'll go
okay,
for a
great.
summary. For the appliances, then here is a sector where similar for automotive. Here we are looking for solutions that are very cheap because for appliances here we go for kitchen hood, fume extractor, a washing machine, dishwasher, and so on. For this, we have developed a solution which is called Metapanel absorbing, basically some micro-perforated layer with a backing cavity. What is the issue here? That standard solution that are used, the use is they use basically melamine foam, which is an absorption foam, and they cover it up with a layer. So they want a very good solution, which is called melamine. Probably you know it. Melamine is very good in absorption, acoustic absorption, but because of fumes, dust, grease, and so on, they need to cover it up with a layer. Therefore, you choose a very good solution, but then afterwards you cover it, you basically spoil all the acoustic performance. In fact, you can see it here, for instance, in the graph, the absorption, acoustic absorption, the melamine foam rises and it's increasing kind of steadily with the frequency, and one basically is the maximum absorption, zero, okay, slow absorption for low frequency, but it's normal. When you cover it up with this layer, you get just a bump of absorption around 2000 Hz, and then afterwards the absorption is very low. Therefore, it's not really an ideal solution. Here, the thing is, mostly for appliances here, we're looking for absorption, so acoustic absorption and reduction of the noise, and not isolation. And the solution is to be modular for sure, washable, fully recyclable, and yeah, of course, performant. The challenge, of course, costs, manufacturing, HSE compliance or health-related compliance. Uh, as said, we have created this solution, which is a micro perforated panel with a backing cavity. Why we chose this backing cavity? Because this can shift the absorption coefficient where we have the most, let's say, critical or annoyance in the frequency. And this enables us to tune our solution to really to fine tune and to address more specifically the noise that we are looking for. How did we do that? Also here, the solution, given that is really cheap, I mean, we needed to find a manufacturing process that as well is really cheap. It's made out of, let's say, a continuous process with, say, cold micro perforation, so in layers, one as well as injection molding for the backing cavity. And this enables us to, for instance, apply this solution in kitchen hood. This is with a typical, a very well-known kitchen hood manufacturer in Italy. It's called Elica, and we could reduce the noise for the noise emission of a kitchen hood appliance by from 2 to 5 dB. It depends on the rate, the work rate of the machine, but this is the peak that, thanks to our solution, we could kill. Therefore, you get a more flattened spectrum, and having a more flattened spectrum, you get better noise better noise quality of the solution. So again, once again, this market segment is the prerogative. The topic of this market segment is that it's very competitive in terms of cost. Therefore, our solution needs to be competitive as well compared to the standard product. And again, here also different from automotive. It's a different type of material, different type of technology. Therefore, you need to rely on plastic or aluminum, for instance, for the manufacturing of this solution. To summarize, we have explored three verticals: infrastructure and transportation appliances. Each of them has its own type of material and production process. And if you look at the overall performance metrics that we saw at the beginning, of course, we always look at the beginning in terms of performance, but there is a big part of the design which relies on cost, material, manufacturing. For the innovation guideline that we have learned on the field is, first of all, you need to comply with the material which is currently used in the sector. This already saves you a lot of headache. You need to comply with the correct manufacturing process. This really enables you to already bring the solution into the market. And then, of course, design an efficient metamaterial solution, taking into account these two bullet points at the beginning, and then, of course, iterate to make it cost efficiently. I know there are 4 bullet points that could be quite obvious at the end of this presentation, but this is, let's say, the guideline that we keep working, iterating every day for making this metamaterial solution, let's say, a reality. With this, I thank you for your attention. I think I've been a bit longer than expected. Don't know if there are specific questions in these remaining times, but I'm happy to reply to your question, or if you have any questions, you can drop me an email later on. No problem.
Thank you very much, Luca, for your presentation. It's actually okay. We also answered a couple of questions during the presentation, so I guess we are
Yeah.
time. So, are there any questions from the audience online? You can unmute yourself and ask any questions to Luca. I don't see anything, but I can ask maybe a question. You said that like the goal of the company is in reality to increase the TRL of certain solutions, like take it from like one level, let's say, and bring it to something that is closer to application, right?
Yeah. Yeah.
So do you have like collaborations with institutes or universities where like you take, let's say, their solution and try to increase the TRL, or is it solutions that you have already developed in the past and you are now working on like increasing the TRL?
Yeah, that's a very good question. So we work we work in both directions, in the sense that there are projects in which there is a company that comes and says, okay, I have this solution, how can we make it better? Therefore, we already start with a certain TRL, which is quite high TRL because it's already a product. We modify the product, we insert the material, metamaterial solution in it. And this is, let's say, option one. And it is quite short term, means that can last from a few months, the project, until let's say, maximum 1 year. There is also the other aspect, which is more medium long term, which is the collaboration that we do with, for instance, with university in the framework of research projects or European project and so on, which we look for new solutions. So we start from a lower TRL, or from a concept, and then afterwards we engineer, we improve it, taking feedback from, let's say, customers, from the market, and so on. And typically there we have in our group we have PhDs that are working, say, in for European project, but as well as we work on a specific problem, and they develop these things. If this replies to, I guess,
No, that was actually my question, because I guess like you may already, like when you started, I guess maybe you already had some projects, but I guess this evolves, and I guess you still have your collaborations with universities.
Yeah. But maybe my question for you is, yes, please, Vasilis.
Sorry, Luca. What about other, let's say, applications which are actually quite important in vibration suppression, as for example, industrial, let's say, areas, rotating machinery and stuff like that,
Yes.
you know, where we have, let's say, these anti-vibration mountings and stuff like that. Is this something, let's say, that Metamaterials can be competitive? Or the markets, let's say, it's so mature and the materials are quite cheap and effective?
It's a very good question. I didn't have time in this in this presentation to show, but basically we have worked and we are working also industrial machineries for the couplers or using the vibration that comes from, for instance, the panels of machineries that can lead to, let's say, the transfer of vibration somewhere else. Therefore, we have solutions also for that, and it is quite big market, and we are in it. Therefore, to reply to your question, the metamaterial could be an integration to the current material, but as well as that they can replace the current material, because we have shown that adding the metamaterial in a strategic way, they can be more effective than the current solution.
Nice. Yeah. Thank you, Luca.
I have a question for you, and it's more related to the previous question about the low TRL, and then let's say the collaboration with the universities or a research center and so on. My question is, if you are working on metamaterials and you are looking for, let's say, an industrial partner that can say contribute and work together with PhDs and so on. As said, we are open to that, and we're actually looking for, say, collaboration in this sense. So if you have something in mind, I don't know if your previous question was somewhat hinting to that direction or it was just curiosity.
No, for me it was curiosity. Vasilis maybe is more because he has worked
for
actually
me,
on metamaterials.
Yes, I know that already. Look, I mean, I have this in mind. We are actually around February. We are starting a new Marie Curie together with Andrea Colombi. We will have 2 students, and I guess that the topic is a little bit flexible. So this is something, let's say, almost immediate, on which we could, let's say, discuss within the next weeks based on what you have presented.
Sounds great.
And apart from that, always, I mean, you know, seeking, let's say, funding and stuff like that will be also something. I know that Horizon is a little bit, you know, you put much effort and the success rates are very low. But I mean, we can try bilateral, let's say, actions between Italy and Switzerland. They're always coming surface. Or in a Swiss projects. I mean, something that we can start digging, let's say, on a more systematic way, actually.
Great, I agree.
Super.
Okay.
Thank you so very much. It was very nice presentation, because, you know, we are, let's say, completely on the academic side, and we just actually presented something that is, let's say, have been constructed, manufactured, and an end-to-end, let's say, solution of something that many people think that is a science fiction, right?
Indeed. But every time the first question we get, amazing, works great, but how much does it cost?
That makes sense, I guess.
That is the first question that we always get, and then we have to explain.
Yeah, that's the case always with new, let's say, solutions, I guess.
Yeah, exactly. Okay, yes. Thanks a lot for this opportunity, and say hi to Eleni, and we'll then catch up soon, Vasilis. That's for sure.
Yeah.
And have a nice day. And
thank you very much, Luca, for the talk. And yeah, have a good day.
You too. Ciao, ciao.
Bye.
Thanks.